All right, class, let's dive right into the training. We are going to be completing the sections or completing our sections on inverter based, battery based inverter. We're going to be completing that sections, and we're on page 14, and now we are on page 15. We were talking about parallel stacking, inverter parallel stacking. They say increases system power at same AC voltage. May provide redundancies if single inverter fails. Parallel stacking does not ensure the whole system wouldn't shut down. If there is a single inverter failure, system may need to be reprogrammed to continue operations. Now, if you look at the parallel stacking example, we have inverter quantity, three inverters. The inverter wattage is 5,000 each. The inverter AC voltage 230 volt. Total system power we have 15,000. Now when you look here, the wattage increases is add up 3 times 5 or 5,000 times 3, that's 15. But the volt remains the same. Even though we have compounded three inverters in parallel, the volt did not change. The volt did not increase. The volt remained the same. It is the wattage that add up. Okay? In parallel stacking. Stacking inverter in parallel increase the AC power of the system while maintaining the same output voltage. This is require once loads and other AC charging source excelled the size of commonly available inverter. One advantage of this type of systems is the redundancies it provides. If one of the inverter fails, if one of the inverter fails, second, um, all right, let's proceed. Sorry, I have some unorganized or informal items in my presentation, and I don't like that way. Now we are all set to roll. Now, some example of parallel stacking configuration include three 5,000 watts inverter that output 230 volt for a total system power of 15,000 volt at 330 volt, similar to photo on the slide. I just explained it and I just show you the illustrations. Notice when you parallel stack the inverter wattage add up, but the inverter voltage remain the same. Something to keep in mind. Now, series stacking, when your inverter is in series, provides split or three phases power, large loads, motor, well pump, long distance distributions. To utilize split or three phase power for battery charging from an AC coupled grill direct PV inverter or generator, 3 inverter quantity, inverter wattage is 3,000. The inverter AC volt is 120. Now, if you look right here, total system power, we have 9,000 watts, the wattage add up. We have 120 volt by 203 watts, 120 volt by 203 volt. Second line, we have 2,500 watts inverter, three of those. The inverter AC voltage 230 volt. The watt added becomes 7,500 at what? 330 by 400 volt. Now let me read. Multiple inverter can be stocked in series, which changes the output voltage in order to generate split phase of three phases. AC power from the inverters that are not capable of producing three-phase, three AC, and capable of producing these AC output individually. This is typical in order to utilize split or three-phase power from an AC charging source such as the grill, an AC coupled inverter, and or a generator for battery charging. Series stacking may also be done because there are large loads requiring this type of AC power, such as the motors and well pump, and because the AC power is being sent long distance, which is done more efficiently at high voltage. Less voltage drop for a given level of current. Series stacking inverter can also be parallel in cluster to increase the power. 3000 watts 120-volt inverter connected in series to provide 3000 watts, 9000 watts. At three phase 120 to 208-volt. We had 200 2500-volt, 330 2500 watts, 230-volt inverter connected in series to provide 7500 volt at three phase 330 by 400-volt. So what it's saying here is if I was doing a grid direct system, I mean, if I was building, um, if I was building a microgrill system, say I was building a small hydro, a small solar farm, for example. Say I was doing maybe a 5,000 watts solar farm to supply a whole community, and I have a couple of inverters. I can stack the inverter in series to increase my voltage, so that when I am distributing my current, I will have I will not lost current or lost power because of long stretch in terms of distribution. So it's a good idea if you are doing a system wherein maybe you're in a compound and the buildings are far from one another. You can pair your inverter in series to increase the voltage. So you notice that the voltage increase from 120 to 208, from 230 to 400, from 120 to 240. The voltage increases. That's what it's saying here. The term series stacking of inverter can be a bit misleading because the inverter are not physically connected in series like a PV model with the positive of one inverter connected to the negative of another inverter. Instead, the output of each inverter goes to a separate phase of the AC system, which creates a multi-phase system. Okay, that's self-explanatory. Yeah, we have a series stacking chart. We have a diagram of a series stacking chart right here. When you look over on this draft here, on this diagram, we have 120 by 220 volt generator, 120 to 220 40-volt generator. And we have right here, we have two phases. We have the neutral, we have phase one and phase two. And running to our AC output, AC input phase section into the inverter number two, 120 volt. Now, then we have another inverter number one here, also going in here, going into our inverter, running into this junction box. We notice that we have the two phase going together into that box from number one to number two. Each inverter provides one of the two length of legs of 120 volt for the 120 to 240 volt system. We'll explain this further. Here is a simplified wiring diagram of two series stacking 120 volt inverter charger with a 120 volt 120 to 220 volt generator also part of the system. This configuration allows full advantage to be taken of the charging source. Note that network communications are necessary, but not shown in this diagram in order to sync the voltage and current output of the inverter. Stacking has the, stacking has the additional benefit of the inverter or charger being able to operate individually, depending on what is happening on each legs of the AC power. For example, if one legs of 120 volt is heavily loaded and the other AC legs is lightly loaded, the charger on the heavily loaded legs can back off battery charging to prevent overloading the generator, while the lightly loaded leg can continue to charge at full output. This is not possible when a single inverter produces 120 to 220 volt. It will have to back off the entire charging to prevent overloading to the heavily loaded legs. Some inverter can even be connected in large group of four or more inverters in what is called the series parallel configuration or multi-cluster configuration. So if you notice in this diagram here, unlike connecting PV models, you or battery, you connect them together in order to form a series connections. When it comes to inverter, inverter number one has it feeds. Here, number one line, you got the red line going up, and we had number two going up into this conjunction box, into this junction box. So they all meet in one box. The feeds, the legs are going in there. We're not connecting the inverter together practically, physically. No, we're not. All right. Stacking inverter must communicate. When more than one inverter is connected to the same load panel, the inverters must communicate to stay in sync. If not network and or communicating, current and voltage will be out of phase between inverters, could cause serious damage to equipment. True true for parallel and series stacking. Consult manufacturer for configuration, additional equipment, programming requirement. Additional communication, wiring, and photo and potentially hardware like data communication hooks are required to enable the inverter to sync their output to load in series or parallel stacking configuration. If the inverter are not communicating properly to stay in phase with one another, the voltage and current will be out of phase and can destroy equipment and loads. As always, carefully read the installation manual for the equipment to ensure that all the required part and pieces are ordered and installed correctly. Series stacking inverter may require a transformer that can balance load on the split or the separate phase as well. Note only note only is the proper hardware required, but the system would need to be programmed to make sure all the equipment works together properly. Now look at the consideration for installing single or multiple inverter. The required output voltage, three phase, the power requirements, more than a single inverter can provide, the redundancies, the space constraints, the size and weight of inverters, additional equipment or structure requires, wire size, number of breakers and disconnects, price include balance of system, bus equipment. When you look at this diagram here, there are multiple inverter in this room, multiple, multiple inverter, and all of this inverter can be synced in order to create a one system. So they're not working individually; they have been synced together. In large system, there is often the options or even the need to choose two smaller inverter or one large inverter. Many factors must be considered to decide which configuration is the most efficient and cost effective for the specific system. It is important to consider the desired AC output voltage. Multiple inverter may be required to generate 120 to 240 volt split phase or various three-phase output voltages. Depending upon the manufacturer, cost is another consideration. 1500 volt wax inverter are likely to be more expensive than 3000 watts inverter, specifically when the balance of system bus and installation costs are factoring in. With only one inverter, system programming is similar, and there are fewer breaker and disconnect required. Additionally, a large inverter will operate at lower efficiency if it is only powering load at level much lower than its rate capacity. In times of very, very low or no power demand from load, all inverters have steady or energy consumptions, and the inverter itself must be considered as a load regardless of the inverter selected. Two small inverter may be a better fit than one large inverter, and in some cases, two or more large inverter may be required to meet the VA demand of concurrent load. When two or more inverters are employed, there is substantially more programming required, and a more communication hub for two inverters is needed as well so they can synchronize output and work more efficiently together. This type of system can be configured so only one of the two inverter operates at low load level, while the other stands ideal with a low standby loads. In this configuration, the second inverter comes online when load demands increases past the capacity of the first inverter. By running only one inverter at small load level, the inverter efficiency will be greater. With two inverters, there is also the luxury of having some redundancies. If one single large inverter fails, the entire AC load goes down. With two inverters, there will still be limited AC power available in the event that one of the inverter fails. This is a perfect illustration, perfect reading. What they're saying here, if I was building a 10,000 watts, 10,000 kilowatt system, ideally I could use a 10,000 kilowatts inverter, but it's also advantageous and it's also advisable to use two smaller inverter, two 5,000 watts inverter of the same manufacturer that can be synced. So instead of having one big inverter that when that one big inverter has a problem, my whole system go off. Now there's no current, there's no source. I can have two smaller 5,000 watts inverter. And these two smaller 5,000 watts inverter, they work in concurrence. So let's say, for example, if I'm using only if the house owner is only using smaller load, it will be running on one inverter. If they add the demand for higher load, so they start adding the air conditions and other big loads on the system, then the other inverter kicks in to give me the additional power that's needed to run those appliances. So in the instant wherein one inverter fails, I can still use one inverter to run the smaller power in that home until we can have a replacement of the inverter that had a problem. So it's better than having one big inverter that in case in a scenario where there is a problem, then they have no inverter to invert the DC load to AC load for that configuration or that system. I can talk very loud because it's 2:47 a.m. in this, and then mine people are sleeping. All right. Now choosing one or two inverter for a 120 to 240 volt split phase system. Now look at we have the total design VA. We should know what that is now. 5,500 VA. The AC configuration is 120 to 240 volt, 60 hertz. Now we had a DC system for 48 volt. The total surge is 8,000 volt. The desired feature generator auto start. Now look right here. We have two outbacks inverter right here. Outbacks. No, so let's see. When selecting an inverter model or deciding whether to use two small inverter or one large inverter, the main the main site parameters to consider are the two design VA, are the total design VA, the required AC voltage and frequency, the DC system voltage, the estimated surge VA required, and any additional features needed for the specific installations. Now, in this example, there is a total design VA of 5,500. Okay, we agree. With a requirement requiring a 120 to 240 volt 60 hertz supply, and the system voltage is 48 volt. The estimated AC surge requirement is 8,000 volt, and the system require an automatic start system for a backup generator. All right, I'm gonna go further. Comparing inverter options, one or two inverter. Now we look here. This is an example. We have our system load, Shannon's, the Allback, Magnon. Total design VA 5,500. Total surge VA is 8,000. We have Shannon, we have Allback, we have Magnon. The continuum power, we have 6,800 VA. That's Shannon. For Allback, we have 3,600 VA. For Magnon, we have 4,000 VA. The surge power, we have 12,000 VA for 60 seconds, and we have 8,500 VA for 30 minutes. What is the surge seconds? It's very important to know. The surge seconds talk about that's the second it takes for the motor of a refrigerator to pick up. Boom. That's the surge seconds. So it's very important to know the surge second when you have loads on the system that have surge powers. Okay. Now we look at the up back 5,400 VA for 5 seconds, 4,000 VA for 30 minutes. Then we have 8,500 for 5 seconds at Magnon. The waveform, we have sine wave, we have sine wave, we have sine wave. Perfect. The battery voltage, we have 48, 48, 48. The AC voltage, we have 120, 240 volt, 120 volt, 120 volt. The adding drawn, 8-watt surge, 28 volt or no load. 9, 34, no load. 8, 25, no load. Now we come down to number of AC input. You can have two, you can have one, you can have one. All right. This table compares three inverter charger model that could be employed in this example. 5,000 watts VA needed for a continuous power and 8,000 watts VA needed with surge. The choice is between using one Shannon XM684 6848 inverter charger, two Outback inverter charger, or two Magnon inverter charger. A continual operating capacity of at least 5,500 VA is required. The Shannon inverter charger is rated at 6,800 VA. A single inverter is adequate. Two Outback inverter will be required, capable of producing 7,200 VA, and a two 120 volt inverter will be synced in series to produce the required 120 to 240 volt. Two Magna inverter will be required, capable of producing 8,000 VA, and the two 120 volt inverter will be synced in series to produce the required 120 to 240 volt. 240 volt. We could use one Shannon, or we could use two Outback or two Magnum inverter. Simple. A minimum surge capacity of 8,000 VA is required. The Shannon inverter can handle up to 12,000 VA of a surge for 60 seconds. The two Outback inverter will provide 10,800 VA of surge for 5 seconds. And the 2 Magnon inverter will provide a 17,000 VA for 5 seconds. So all inverters easily meet the surge requirement. All three inverters also produce a quality sync wave form and are designed to work with a 48-volt battery bank. They all can output 120 to 240 volt. All three inverters have a feasible ideal drawn. When no loads are turned on, the Shannon will draw 28 volt. Each outback will draw 34 volt, 68 volt, and each Magnon will draw 24 volt, 50 volt. All three inverters also have a search mode, which allows the user to configure settings that let the inverter sleeps when no loads are present, reducing the ideal I draw. The total surge load for the single Shannon's inverter charger is 8 volt. It is 18 volt for two outback inverter and it is 16 volt for two Magnon inverter. The Magnon outback inverter only have one AC input. This is where the grill or a generator, but not both, can be connected to the inverter charger. The Shannon can accept two AC inputs so it could take advantage of charging from both a generator and a utility grill if they were available. The CEC rate efficiency for the Shannon inverter charger is a little than that of the Outback and both are quite a bit better than the Magnon inverter. An additional factor to consider is the weight. A single Shannon inverter is substantially heavier, which could make installation more difficult. All three of these inverter configurations will work for this system design. In deciding which one to use, all of these specifics should be considered as well as available price, reliability, possible expansions, and customer installation preferences. AC battery charging considerations and maximum charging rate can be internal to inverter or external battery charger. Can be internal to the inverter or an external battery charger. Common AC source generator or grill direct PV inverter. Determine the maximum battery charging rate. 3 bottlenecks. How much current can battery bank accept? What is the maximum battery charging pass through? What can AC charging source provide? If charger maximum charge rate, battery maximum charge rate, program charge to limit charge current to battery. Another factor to consider in the process of specifying a standalone inverter is the capacity of the internal battery charger. It's very important. Yes, I had a scenario with this. Often generator will have a higher output ratings than the inverter battery charger can fully utilize. In some cases, the system designer will specify a much larger inverter charger than is required to operate the AC load. In order to increase the charger capacity, which will reduce the amount of time that the generator has to run to recharge the battery, thus saving on fuel costs, pollutions, wear and tears on the generator, and noise. With some generators, especially large ones, the only way to ensure adequate utilization of its output power is to use a multiple inverter charger. This is especially common when the generator has a three-phase output, which usually requires three inverter or charger to be stacked. Another option is to use an external battery charger size large enough to handle the available power from the generator. In some situations, the inverter or charger has a higher maximum charge rate than the generator is capable of providing. In this situation, it is important to program the inverter to reduce the maximum charging rate in order to avoid overloading the generator. If the inverter or charger is if charger tired, tries to charge at a rate that the, that is higher than what the generator is capable of providing, it will cause damage to the generator. So if we have a system, if you build a system and you are expecting to be able to use your generator as a standby during cloudy days or days of a tournament, you must take into consideration the charging capacity of your inverter in line with the generator capability as well, or capacity as well. Because one way or the other, you don't want to overload the generator, and you don't want to break down the generator trying to charge the batteries. So you must, as a designer, these should be taken into consideration seriously. AC battery charging minimum charging rate. Now for non-lithium battery, lead acid NIFE, typically 10% of CO20 value. Example, the battery 20 equals 550 amps. The minimum charging rate, the C20 times 10, 520 amps times 0.10 equals 55 amps. Now, less charge current may be used, 5% to 20 through this, though this will increase the required charging time and increase the potential for sufficiency in lead acid battery. Configure with battery manufacturer. Confirm with battery manufacturer. You have to check the charging rate of the battery. That's right. Lithium ion. Many manufacturers state they do not have a minimum rate, or it does not matter. Confirm with the battery manufacturer. Now, for lead acid, it is important to check the manufacturer or information from the manufacturer as to the charging rate. But for lithium ion, most of them don't really have charging rate. They don't. Some battery types like lead acid or nickel ion have a minimum charging rate, which is designed to prevent the battery from becoming chronically uncharged, which will reduce the battery life. The minimum charge rate is typically represented as a percentage of the 20 hours capacity of the battery bank. In the example on the slide, the battery is rated at 550 amps hour at 20 hours rate. The minimum charging rate is 10% of the C20 capacity of 550 amps times 0.10 equals 50 amps. If this was a lead acid battery, it will require at least a 55 amps charging rate in order to prevent sufficient, which is the build-up of software on the lead plate, which reduces the battery capacity. If a lower charge current is used, it would increase the charging time because the battery is charging more slowly and the battery lifespan may reduce. The minimum charge rate will vary by manufacturer, so be sure to read the specification sheet and manuals. Some battery type like lithium ion may have no minimum charging rate, so a low charge rate will have a little to no effects on the battery. Again, be sure to confirm minimum charging rate with the battery manufacturer. All right. Inverter internal battery and charging capacity. Generator output ratings, the battery charging ratings, general output rating, battery charging rating. Solution. Use larger inverter. Use more inverters. Use a separate extended battery charger. Reduce generator runtime. Better utilize generator. Okay. When sizing a battery-based inverter or charger and generator, it is important to compare three maximum charging rate. If the generator has a higher output rating than the battery charger a maximum charge rate, then the capacity of the generator may not be fully utilized. Solution would be to specify a large inverter or more stacking inverter, an external battery charger that has a higher maximum charge rate could also be used. By matching the generator output rating and maximizing the charging rate, the generator runtime will be reduced because the battery can charge faster and the generator will also run more efficiently. If the generator output rating is less than the battery charging maximum charging rate, then the inverter will be programmed to charge at a reduced rate. Another option would be to reduce the load while the generator is running in order to use as much current from the generator as possible for battery charging. If the charger calls for more power than the generator is able to deliver, a generator may be damaged. One benefit of having more charging capacity than the generator capacity is that the generator will operate closer to its maximum output, which typically is more efficient. Specifying battery-based inverter, we have the battery charging volt, the battery charging maximum current ratings, the absorption time, the temperature compensations, the low voltage disconnect, LVD settings, AC input settings, the generator or grill direct. Example battery voltage set point, battery type, floater lead acid battery, charging voltage setting 48 volt, bulk absorbed 59 to 59.2 volt, the float 52.8, equalizing 64.04, 64, 64.0 volt. For lithium ion, we have 48 volt, 55.2 volt, 55.2. Done the equalizing, 55.2 volt. Nickel and ions, nickel and ion 38 cells. Nickel and ion has 40 cells and 38 cells, and the volts are there. So the inverter charging set point. Battery-based inverter and charging system have numerous set points which need to be adjusted for proper system operations. The most common settings are the battery charging setting point, like a solar charge controller. These must be correctly set for the type of battery used. All right. My coughing. All right. You can read through that. You guys will have copy of the material. The AC load control, load shading relay of time can be used to shift load. I'm going to try to sum this up. The multi-wire branch socket, safe wiring, inverter 120 to 240 volt output. The split phase 120 to 40 volt. Supply enter load center. 15 amps double pole breaker. Supply multi-wire branch socket. Current on the neutral will not exceed. Current rating of conductor. We have 120 by 240 volt. The multi-wire branch socket single neutral service 120 volt socket only and 220. The waveform center. Multi-wire branch socket at socket in 120 to 240 volt system where line 1 and line 2 share a common neutral conductor, as shown in the diagram. This is sometimes done when wiring lighting an outlet socket in a home as an effort to save a small amount of money on wires. A common type of interior wire called the NM cable is often used. One well-known branch is Romex, and in this case it will include two hot conductors, typically one black and one red. A single neutral conductor, typically white, and a ground wire, bare copper or gray. The multi-wire branch socket are only safe to install on 120 to 240 volt load. Centers that actually have a 120 to 200 volt VC supply with a 120 volt line and a separate 120 volt line to feeding separate buck bags in the panel. This diagram shows the safe installation of multi-wire branch socket. As you can see the diagram right here, very self-explanatory. You have your AC box. This is the AC box. We have a 120 volt output here. We have our wave sink, right here into your sockets in your wall. This is a split phase 120 200 volt multi-wire branch sockets. Very explanatory when you read this. I unsafe wiring. Now look at the difference. This wire is consists. This diagram shows a safe way to wire your circuitries. If we look at here, this is very unsafe. Very, very unsafe. Unsafe. The waveform are in sync. Here, our waveform cancel. Here, the waveform are in sync. Neutral is 30 ohms. Neutral is greater or equal to 50 ohms. So my technicians take note of that. Single lead of 120 volt enters load center. Bus bar jumper to utilize all breakers. Require limit. We have a 120 volt. We have our jumpers, supplier, bus bar breaker. Code does allow for 120 volt system if there are two multi-wire branch socket, and if a warning limit is placed on the main load center that reads warning single 120 volt supplier do not connect multi-wire branch socket. If this building is if this building is new construction, it should be easy to make sure that no multi-wire branch socket are installed. If it is an existing building, it is important to do some details investigation to ensure there are no multi-wire branch socket in the building. Also keep in mind that installing a jumper between line 1 and line 2 in the load center may involve the listing of the panel or it logs. Be sure to verify with the manufacturer that installation jumper across the box bar is acceptable. This is our quick summary. What information is required to specify a standalone inverter? What is the difference between continuous power ratings and surge ratings and a standalone inverter? Explain difference of parallels and series inverter stacking. What is multi-wire brain socket wiring and describes the concern in 120 volt system. What information is required to specify a standalone inverter? In order to specify a standalone inverter, the following information is required. The normal battery bank, the volt, the AC output frequency, the hertz, and the voltage, total design VA, total surge VA, and any additional features that are required, such as the generator input or auto generator start functions. What is the difference between the continuous power ratings and the surge ratings of a standalone inverter? Continuous power ratings is the power ratings that the inverter can produce consistently. Surge power ratings is the amount of power an inverter can produce for a short period of time. Explain difference of parallel and series inverter stacking. Parallel stacking of inverter adds to the power, wax, capacity of the system. Series stacking inverter is used to get the required output voltage like 120 240 volt VA or 120 208 volt. What is the multi-wire branch socket wiring and describe the connect concern in 120 volt system? A multi-wire branch socket is when two load sockets that are hooked to 1 and 2 in the 120 volt system share a common neutral. When they are installed in 120 volt system where the 1 box and line 2 box line 1 box and line 2 box shares the same phase. The shared neutral wire can become overloaded and cause a fire hazard. All right, guys, that's the end of this section uh, on inverter, battery-based inverter. Um, it was a pleasure. My name once again is Ben Sarti. Thank you for your time and thanks for the class. Okay, thank you, gentlemen.